Module 4, Exercise 1. We're going to calculate several spectral indices. And we'll do that again for the ULB area. So I import the asset. I change the name of the variable to ULB. And we're going to calculate the indices from Sentinel data. So I'm going to import the Sentinel-2 data from the image collection. And I'm going to copy the collection snippet and create a new variable s2 equals, and then I paste the snippet which imports the image collection. I'm going to center the map at ULB with a zoom level of 10, and I also need to end that line with a semicolon. Now let's filter the data. Use the image collection and then filter, and use EE filter. And we're going to filter on the cloud cover. It should be less than 30%, as we've done before. We use the metadata cloudy pixel percentage and the value of 30. We'll also filter on date. And I'm going to calculate the indices for the year 2020. Take 1st of January until 31st of December of 2020. And I want to filter on the boundary of the study area. And therefore you need to convert the ULB to a geometry. Otherwise it will not work. Make sure you have enough brackets there and end the line with semicolon. Now I want to calculate these indices on the best pixels in the year, so I'm applying the median function. And let's first look at the image that we now have filtered. So I define a variable for the visualization, RGB_viz, and define the dictionary with a minimum of 0, maximum of 3000, and I want it in true color, so I use Sentinel band 4, band 3 and band 2 for RGB. End with semicolon. And then I'm going to add the layer. So we can already have a look at our layer from which the indices will be calculated, and we add here .clip ULB to make it only fitting our study area polygon, and I call it image. Let's run this, and there's our best RGB image of 2020 for the study area. Let's calculate the first index, and that's our popular normalized difference vegetation index, or NDVI, which uses the near infrared band 8 and the red band 4. We define a variable NDVI, and we derive it from image, and then we use the function normalized difference, which needs the band names as a list. Square brackets for the list, and then band 8 and band 4. And I need to give the output band also a name, so I use .rename, and that's NDVI. Now let's define how we want to visualize this. NDVI goes from -1 to +1, but from 0 to 1 is vegetation, so let's scale from a minimum of 0 to a maximum of 1 and give that a color from white to green. So the more green, the more vegetation. We define that with palette. So if you have a multi-band image, you use band, like we did for the image before. And if you have a single band pseudo-color one, we use palette. And we can simply type white and green in the list to have the scale from white to green. Well, let's add the layer and clip it also to the ULB boundary. Use NDVI_viz for the styling and call the output NDVI. End the line with semicolon and run. It runs in the order of the lines, so it's not like in the layers panel of GIS that the bottom one is also the bottom one on the screen. So here the first map.add layer will be the first one added, which is our median filtered image. And then we add on top of that, after the calculation, the NDVI. Let's calculate another index, the modified normalized difference water index. And with that one we can find water bodies, and it uses the green band, which is band number 3, and the shortwave infrared 1 band, which is band number 11. So similar to NDVI, I define a variable MNDWI, and that is image.normalized difference, because this is also a normalized difference index. And in the list I give the bands 3 and 11, and I rename the band to MNDWI. And I also define the visualization here. I use a minimum of 0 for no water and 1 for water. And we use a palette, white for no water and blue for water. Let's add the layer in the same way. I'm going to make comments of the other one, so we only see this latest output if we run it. Gives that error, but that's not important. And there's the result. Now we can also have indices that are more complex and not just a normalized difference. So let's look at the example, the Soil Adjusted Vegetation Index, or SAVI. And the equation is 1.5 times the near infrared minus the red band divided by near infrared plus red plus 0.5. For these kind of indices we use the expression function. In this case we also need to use reflectance values, and therefore we need to convert the numbers in the bands, the pixel values, to reflectance by multiplying it with a factor. So we're going to make this equation, new variable SAVI equals, and then image dot, and now we use expression, and we split it over the lines to make it more readable, and we need to put the equation as a string. So 1.5 times near infrared minus red divided by near infrared plus red plus 0.5. And now we have the whole equation in a string. And now in a dictionary we are going to define the variables in the string. So near will be the correct band which we select from the image collection. So image.select band 8. And then multiplied by the factor 0.0001. Then we define red, which is image select band 4, multiplied by the same factor to get the reflectance. And we rename this to SAVI. And we will use the same visualization as NDVI, because this is also a vegetation index. So we use NDVI vis. So for the assignment, you're going to calculate other indices. Good luck!